And we're live.
Hi, everyone. My name is Daniel Kremers. It's a great pleasure to present our speaker today, John Barron from Google. Let me give you a bit of background on John. He got a PhD at UC Berkeley in 2013, former student of Jitendra Malik. Received also bachelor's in computer science from University of Toronto before that. He's received many awards, including the National Science Foundation Graduate Research Fellowship in 2009 and the C.V. Ramamurthy Distinguished Research Award in 2013. Also the PAMI Young Research Award in 2020. He has written a number of very impressive papers. Some of these received awards, including 2 Best Paper Honorable Mentions at ECCV in 2016 and 2020. I've known John for a number of years now, and what I find most impressive is that his work is both very diverse in terms of the topics he tackles, but it also beautifully combines the fundamental challenges of computer vision modeling, shape, illumination, things like that, with all the recent developments in deep neural networks. And so we're very happy to have him here today. Today he'll talk about neural radiance fields. The floor is yours, John.
Thanks. That was a really lovely introduction. I appreciate it. Can everyone see and hear the slides okay? Everything coming through?
Perfect, yes.
Great. Okay, so yeah, I'll be talking mostly about neural radiance fields, and I'll explain what that means later. So yeah, as Daniel said, did my PhD at Berkeley with Jitendra, and I've been at Google since 2013. My manager is David Salison, who some of you might know from his time at Adobe and Snap. I'm in a part of Google research called Perception, which is a parallel track to Brain and other parts of Google research. It's where we handle pixels, vision, and things like that. Yeah, my research interests just over the last decade or so, I kind of started off doing inverse rendering, trying to recover the world behind a single image. This was my dissertation was spent on. At Google, I've done a lot of work on color constancy, the problem of white balancing an image, and a lot of work on kind of motion and depth estimation, particularly in the context of making high resolution and edge-aware smooth depth maps and motion fields. And I've some work on loss functions, generalizing loss functions that people seem to enjoy. You know, at Google, you do research, but you also get to touch products that people are aware of. Probably the most visible kind of product impact that my research has been involved in is the Google Pixel phones, the low light photography modes. HDR Plus is the standard mode. There's also this night sight low light mode. These are techniques for taking lots and lots of images and kind of aligning and merging them together and doing clever tone mapping and machine learning to make low light photography possible. Probably the biggest thing I've done there is the white balance algorithm. Every time you turn on the camera for Google phone, it runs our 2017 CPPR paper on white balance at about 3 hertz. It's also lens blur and portrait mode. These techniques, these applications. I'm sorry, I'm getting some AV problems over here. Please let me know if something starts sounding weird. Portrait mode is a feature in, well, and most phones now, but it was a feature that for a long time only Apple and Google had on their phones, where you take a picture and it does a lot of stereo and machine learning semantic segmentation and kind of carves out the background in the foreground and blurs out the background to make it look like your camera has a very wide aperture. More recently, we just launched a feature called portrait light, which is kind of a similar effect, but it allows you to take a picture of something or someone and move the light around after the fact. And this, of course, involves a lot of inverse rendering and machine learning. I've also worked on Google Glass and Google Jump, two not so successful hardware projects at Google. Feel free to ask me about that if you're curious. But today I'm going to be talking about some different stuff, some new work, primarily around these neural radiance fields, this NeRF project that this was at ECCV this past year and made a big splash. So I'll be giving an overview of how that works and what that is. And then I'll be diving into this follow-up paper that we have that'll be at NeRFs this coming fall, this coming winter. And this is a theory paper that explains why NeRF works. And then I'll be explaining some work we have in preparation called NeRF in the Wild. And this is about making NeRF work not just on controlled images, but on kind of unstructured image collections like you find on the internet. So first NeRF. So NeRF stands for neural radiance fields. Neural because there's a neural network. Radiance because the thing that the neural network is describing is the radiance of a point in space, and that's how much light is emitted and how kind of dense that point is. And field because this is a kind of implicit field of radiance. There's no discretization. The neural network is describing an implicit function that kind of exists everywhere as a continuous representation, contrary to most kind of neural network projects. This was a collaboration between Google and Berkeley. I was the only Googler when it started, but we've since hired Patul onto our team. So what I'm seeing right now is a really wonderful animation of a spinning vase. And I'm guessing you guys are not seeing something quite as nice. How many frames per second is that video running at? Does anyone want to tell me? Anyone?
It's like 15. It's like sometimes smooth and sometimes it freezes. Okay, cool.
If you go onto our website, so there's a URL at the bottom of this page. This is the project page. You will find GIFs and videos of all the sorts of animations that I'll be showing. You can just scroll through on the website. The problem that NeRF is solving is view interpolation, which is taking in some images, like you see on the left, and producing a nicely, smoothly interpolated views on the right. From where I'm sitting, the images on the left are very, it's showing discrete images and jumping between them, and the thing on the, on the left, that's what I'm seeing, and on the right, I'm seeing a very smooth, photorealistic, interpolated views of the camera moving smoothly through space. If you are not seeing that, please check out that link and scroll through. And repeatedly throughout this talk, I will be talking as though the results on the screen are beautiful and smooth and nice and photorealistic, and you'll just have to take my word for it or verify it yourself by checking out the website. So this is what NeRF is trying to do. We're trying to take in some images, produce a model that lets us produce new images, and we're trying to maximize quality there. And NeRF basically achieves photorealistic results for this task. You can see some artifacts if you really look closely on the kind of periphery of the frame, but in general, the renderings from NeRF look really, really good. And this represents like a very significant improvement in quality for view synthesis tasks. There's been a lot of recent work in view synthesis kind of building up towards NeRF, specifically in this kind of world of these RGB, alpha, volumetric sorts of representations. These are models where you're explicitly reasoning about color and density at a point in space in some way. Kind of an earlier work in this space is the soft 3D work, which is kind of like taking a kind of conventional stereo cost volume and just turning that into a RGB alpha volume, and that lets you take that volume and collapse it down to an image and produce nice renderings. This was built upon in this kind of line of work on these multiplane images, which it's the idea that you would take an image or a stereo pair and kind of promote it to this 3D representation that looks like if you were to take a kind of your camera frustum and cut it up along Z and kind of have a slice of dense stuff, semi-transparent stuff at every layer. And then more recently, this idea has been taken even further to the point where we have these neural networks that look at images and then kind of hallucinate 3D volumetric representations like a whole voxel grid. And then you can just shoot rays through that voxel grid and do normal graphic stuff and get very nice renderings out. This line of work is really promising and impressive. In particular, this volumetric approach is great for optimization, because volume rendering is a very nice, smooth thing to optimize as opposed to kind of differentiable raster graphics engines, which is another thing people have been pursuing. The real problem with these things is that they have horrible storage requirements, because if you wanted to make a high resolution image, that means you need a high resolution voxel grid, and storing a voxel grid with enough density in it that you can reconstruct a 4K video feed is basically intractable. And this gets even worse if you start considering view-dependent effects, which add additional complexity. In parallel to this line of work, there's been a lot of equally exciting work, I'd say, on this task for this idea of using neural networks as a continuous shape representation. So most people think of neural networks as a thing that takes in a vector or a grid of pixels or something and spits out some output. This is a different approach where the neural network takes in a point in space and outputs some property of that space. And in this case, this is a kind of occupancy sort of cartoon diagram where we're trying to train a neural network to say, is this point in space inside or outside this bench? So this is very unlike kind of normal uses of machine learning, because your training set was going to be just observations of one scene, like one chair, and the weights of the model will absorb everything you know about the world. The world is represented inside the weights, and there's no notion of kind of generalizing to new objects or anything. The goal is to observe some points in the space and to generalize to new points in that space. There's been a lot of work kind of building on this idea of training networks to represent occupancy or sign distance fields, which is a kind of smooth approximation to occupancy. And then this SRN's work was very well received, and that takes this idea even further. And there's a lot of progress in the space. And these models are cool because they're very small. Like you can really have a very compressed representation of the world. And that representation kind of has no fixed granularity of detail, because a neural network can describe anything. So you don't have to like predefine a voxel grid and cut up the space that way, and then you're stuck with this predefined voxelization. You know, the neural network can move its things around and kind of describe anything. But these approaches are kind of limited in terms of how you could render them. They don't really lend themselves naturally to producing photorealistic renderings in a view interpolation context. So NeRF exists kind of in between these two fields. It builds on both of them. This is the whole model. It's a very simple model. The model that all the results will be showing is just a 9-layer neural network, a standard non-convolutional neural network, like a 1970 style neural network that has 9 layers and 256 channels at each layer. And the input is 5 numbers, a 5-dimensional vector that is just x, y, z, so spatial location, where you are in space. And then 2 more numbers, theta, phi, and that's the viewing direction of that point in space. So how are you looking at that point in space? Where are you looking at it from? And the network takes in that 5-dimensional coordinate and produces as output 4 numbers, a color, an RGB color, and then a density sigma. And you know, color is what you think it is, and density is just how dense is this point in space, and that's a number from 0 to infinity. So if someone gave you, so just to clarify, the weights of this network are just a model of the world you are in. There's no like, you don't train these and then test them. I mean, I guess you do, but we're going to just overfit this model to one world. So probably the easiest way of thinking of this is just in terms of how you would render a NeRF if you already had one. And the procedure for rendering a trained NeRF is you take your camera, you take a pixel in that camera, and then you shoot a ray from the center of projection of the camera through the center of the pixel, and it travels out into the world. This is exactly how a ray tracer works. And in a normal ray tracer, you'd shoot that ray out until you hit something, and then you compute a color, and then you'd return that color. In NeRF, what you do is you take that ray, and then you use the near and far planes of the camera, and they define a range of values, and you just take all a discrete set of samples of points along the ray that lie between the near and far plane. And that's a set of, it's a batch of 5-dimensional coordinates, x, y, z, theta, phi. And you take that batch, you feed it through the NeRF, and it just processes each of these points independently. It's a normal MLP operating on 5D coordinates, and it produces output a color and a density for each of those points along the ray. That's what you're seeing on the right, is a bunch of colored semi-transparent points. Once you have that, you just apply graphics 101 for volumetric rendering, and you just march from the back of the ray to the camera, and you do alpha compositing of each point onto the thing behind it. And when you're done, you have an RGB value, and that is the color of the pixel, and that's it. So this is, the rendering here doesn't involve like a neural network on a grid of pixels. There's no like CNN on an image. The training is just, and inference is just happening independently at every pixel in the scene, and the neural network exists in the world. The neural network is a function of world space coordinates, not of anything having to do with the image or the grid of pixels. So this works really well because volume rendering is trivially differentiable. The color you're going to get is just a weighted sum of transmittance and density and color of all the points in the array. And if you read some graphics papers from the 1980s, you can see how these are defined. It's just some cumulative products and then a thing that looks kind of like a soft plus. This is all great. If you implement this in TensorFlow or PyTorch or something, you'll see that it's very well supported. It's very easy to implement and to optimize. So you can train these models by just doing the simplest thing in the world. You just you shoot a ray out, you get a gradient, you get an RGB value, predicted RGB value for the pixel. You compare it to the observed value in the image that you have, and you backpropagate through volume rendering, and you just do gradient descent on that. And this is all we ever do is just minimize L2 loss on pixels using Atom. And this is super straightforward. Because this decouples into pixels and rays, you can actually, we don't even iterate over images. We just take all of the pixels in an image, we make a bag of them that have a ray associated with each color, and we just iterate through random rays, not random rays, all the rays of the images in the training data, and we cast them out, we get colors, and we do gradient descent, and that's it. You can implement all of this in a Python notebook in about 100 lines, and we have one on the GitHub. It's called TinyNeRF. It's a really nice little test set. You can go there, launch this job up, and by the end of the talk, you'll have a nice 3D model of that Lego truck that you can rotate and play with. So in most of the examples we're looking at, we kind of just have an object in the scene, and we have lots and lots of cameras around them. And we're just going to train to minimize reconstruction loss against all those cameras. This is a very aggressive context where we're assuming we have lots of data. And that's because in lots of contexts we do have lots of data. And this is, for this paper, we were kind of pushing on quality primarily. NeRF has no prior beliefs about what the world looks like. It's a random neural network that's randomly initialized at the beginning of training. So if you give it just a small number of views, it will produce a very bad result. It will not generalize new views. But if you give it lots and lots of views, then it basically, the easiest thing for kind of lazy neural network training to do is to reconstruct a 3D world that explains all the views, and that happens to be the right 3D world in most cases. There's some tricks to getting this to work well. One trick is that the batch size of our training is proportional to how many rays, how many points we drop along each ray that we shoot through the world. So this can be really expensive because you kind of want to evaluate probably hundreds or thousands of those points. A trick for dealing with this, and this is just a standard trick we borrowed from volumetric rendering stuff, is we do a 2-pass stage where the first stage we just lay down points evenly along the ray, and then we ask the NeRF how dense is the stuff of those points at those points we laid down, and that tells us where the front of the object probably is, and then we lay down more points that are distributed unevenly and are focused on where that stuff is. There's a coarse model and a fine model, and we're just training both simultaneously. And this isn't really critical for anything other than speed, but this is an important way to kind of get good sample efficiency during training. And as I mentioned, the input to the model is not just where you are, it's how you're looking at something. And this lets you model view-dependent effects, like non-Lambertian objects. If you deleted the view-dependence thing, then NeRF would be limited to only describing Lambertian objects, and the world is non-Lambertian, so we have this view-dependence. Just adding in these two numbers lets you describe basically any view-dependent effect, except for view-dependent transparency, which is not a very common thing. But so here we have a visualization showing the color that is being predicted by the model for one point in space at 2 different viewpoints. This is one of those figures where if you're used to looking at BRDFs, you can kind of see what's going on, and if you're not, then it's opaque. So don't worry about it. You can just think of NeRF as being fully Lambertian if you want, and you'll be able to understand what's happening well enough. So let's look at some results. So again, these videos look great to me. They might not look great to you. So please check out the website and scroll through. But NeRF is basically able to produce really, really excellent renderings of surprisingly complicated scenes with lots of thin structures, complicated geometry. There's a lot of shiny things in here, and there's a couple of scenes where we have transparent things and refraction, and it actually managed to do a pretty good job of faking things. So yeah, the results are cool. They're very fun to look at. Definitely check it out. Here's a comparison against kind of prior work in this space. This is SRNs, which is, SRNs are doing a lot of complicated things that are kind of more sophisticated than what you need to solve this problem. But it produces, like, it can kind of get the broad strokes of the scene and kind of struggles to get fine details. Here's another scene, another result for SRNs. So it looks like a 3D world, but it doesn't look like photorealistic renderings. We can compare against kind of classic graphics techniques, or the spiritual successor of classic graphics techniques. This is LLFF. It's a technique that takes in images and lifts them to light fields and then learns to blend them together. You can think of it as the spiritual successor to like unstructured lumographs or something like that. And these techniques work surprisingly well in a lot of cases, but struggle at kind of transitions between these areas where they're fusing light fields. This is a comparison against neural volumes. This was a very nice paper from FRL. And they're getting decent results, but this is a technique that's based around having a coarse, not a coarse, but a fixed, discrete voxel grid. And as a result, it's just fundamentally limited in terms of the detail it can explain. And NeRF has a neural network backing everything, so it can get very, very fine details because it can allocate its capacity as needed. Here's more examples. We had this nice Blender data set. We just rendered off ray tracing views of a bunch of objects, and that's how we did a lot of our experimentation. This is not ground truth. These are renderings. I was confused about that when I was making these slides. I mentioned that there's view-dependent effects. So these view-dependent effects are really nice. They let us explain away these very complicated scenes, like the one you have here, where that screen in the background, the TV, you can see the gloss of the reflection kind of moving as the camera goes around. And on the right, this is just a neat trick we can do. We can, instead of actually moving the camera, we can just tell NeRF that we're moving the camera, and then you can see the specular lobes on the table and on the screen move around as though the lighting is moving around, kind of. Here's another example showing that, where you can see on the right the metal parts of the stove. You can see the specular lobe just move back and forth. We can take a NeRF, so you know, a NeRF is not like so much a physical kind of concrete 3D object, but it does exist in the 3D world. It's like it's in 3D world coordinates, so it's kind of geometrically consistent. And so what we can do is we can shoot rays at it and just see where they terminate, and that gives us depth maps. That's a way of getting really nice looking depth maps, and that's what you're seeing on the right here. This is just the expected termination depth according to the transmittance of the NeRF. You can see very clean edges. There's none of kind of the edge fattening you usually see in stereo, and very thin structures that are usually very challenging to get here. Here's another example of a Christmas tree. If you look closely, you can actually see it's making lots of mistakes, kind of 2 layers deep into the tree. It kind of starts to fall apart, but it's doing a good job of kind of faking its way out of that in terms of picking the right colors to kind of paint in the background to make it not look obviously wrong. This 3D representation is neat. We can do cool effects. Here we're just compositing a ball on the scene using just the Z buffer to figure out where to render the ball. And you can see that it's dealing with the edges of the objects, the occlusion edges of the objects very nicely. And we could also do things like just mesh the NeRF. Here we're just running marching cubes on the NeRF. And it's not great because this is not really how NeRF was designed to be used, but it's like pretty reasonable. It produces, and this is just you know, running a standard marching cubes implementation out of the box on a model that was not trained with any idea of what a mesh is, really. So everything I just explained to you about how NeRF works was a severe oversimplification of what's actually going on under the hood. The system I described produces results that look like this, and this should look a lot fuzzier to you, on your end, even with video compression, than the results I was showing. The system I described is not exactly what we want. So we had this one weird trick that was necessary to get really, really good results, like the one you see on the right, and this was this positional encoding trick. So to explain this trick, I'm just going to back off from NeRF and just describe a simple toy problem. You can think of this as like a NeRF-like problem, but I think that's too generous to NeRF. This is something that's called a CPPN. People thought about these models in the literature a little bit as kind of like interesting oddities. So this is a neural network where the input to the neural network is 2 numbers, a XY coordinate, which in this case will be the coordinate of a pixel in an image, and the output is an RGB value, the color of that pixel. This is a weird thing to do. There's really not very many good reasons to train a model like this, but it's a thing you can do, and it's a fun test bed because you can look at it and try things out. And what's really surprising is that if you do this, if you train a neural network to do this, it will not work. It fails very badly. So here we have a model on the middle there. This is a very large neural network with more weights, I think 8 times as many weights as there are pixels in the image. And we're giving it all the pixels in the image and we're telling it to explain them away. We're training on all the pixels in that image and doing gradient descent for a long time, and it is unable to recover the image. And this is super strange, right? Because the neural network has way more parameters than there are inputs. Neural networks are universal function approximators. And there's no unseen data. It has access to all of the data here. So what's going on? We were confused by this, and we came up with a trick that worked, that fixed this. And this was, instead of taking the 2D input, the XY coordinates, which is we're calling V here, instead of feeding that into the network, we take it and we pass it through a series of sines and cosines of increasing frequency, so twice and 4 times, et cetera. So you kind of blow this feature vector up into a high dimensional space with a lot of high frequency wobbling. It's been introduced by this Fourier feature representation. And that is the input to the network. And this is just a fixed function. This is just one line of NumPy. There's no learning here. It's just a fixed function you just add to your network at the beginning. And if you do this, suddenly your neural network can memorize the image. So that's what you're seeing on the right, is just the model very quickly training itself to reproduce the entire image. As it should, right? This shouldn't be hard. It's weird that it is hard, but this is basically like a kind of patch you have to apply to your model to make this work. And so you apply the same trick to NeRF. You do the same Fourier feature kind of expansion or we call it positional encoding in the paper, because that's what people in the transformer literature call it. You apply that to the XYZ theta phi coordinates in NeRF, and you get these really nice high resolution results. So we were working on NeRF, and we had figured out that this worked and was necessary to make things happen, and we didn't know why. We didn't know what was going on. And for a long time, we thought that we couldn't write a paper about this without having a good explanation. But we ended up deciding just to write up NeRF and just kind of punt and say, we don't know why this works. But we immediately set to work trying to explain to ourselves what was going on. And that led to this follow-up paper that we have. That's going to be at NeRF's in the winter. And this is one of those papers where the title is the takeaway from the paper. So Fourier features, which is what we're calling this sinusoidal decomposition of a coordinate into higher dimensional space. These let neural networks learn high frequency functions, so functions with lots of high frequency detail, in low dimensional domains like 1D or 3D or 2D, like we were showing. So here's a cartoon visualization of what NeRF is doing, right? You've got an input coordinate V, which is a very short vector. For NeRF, it's just 5 numbers, x, y, z, theta, phi. And then you feed that input vector into a fixed input mapping function that we're going to call gamma. For NeRF, this was positional encoding, the powers of 2, and we're showing that here. So this takes phi and projects it onto a bunch of axis-aligned sinusoids with frequencies that are powers of 2 from each other, and also lifts it up into a higher dimensional space, though that's less important than you might think. And you feed that positional encoding into a boring old ReLU MLP F, and you get the output, which is just a single color and a density. This positional encoding function has a single hyperparameter that we noticed was very important, this L value here shown in a red box. This determines how many levels were in the positional encoding, which is also the highest frequency that's used by the positional encoding. And this is basically a knob for regularizing NeRF. If it's too low, we saw that things over smooth, and if it's too high, you start to see noise and floaters and things like that. So after staring at this for a while, we realized that positional encoding was the wrong sort of thing to use, and it was strictly better and cleaner to just use random Fourier features. Positional encoding is kind of a special case of Fourier features. So we're just going to generate a big random skinny matrix B and project V onto it and push that projection through a sinusoid. This is a classic technique for kernel machines and kind of straightforward discriminative learning. There's a lot of nice work on these sorts of features that we were able to take advantage of to understand what's happening here. The classic citation is Rahimi and Recht, highly recommended, great paper. So these random Fourier features also have a hyperparameter, and that's the standard deviation that you use to generate the matrix. And that serves the same sort of purpose as the number of levels in the positional encoding. So to understand what these Fourier features are doing, we found it super useful to bring in ideas from the neural tangent kernel literature. For those of you who aren't familiar with this, NDK is a really remarkable result that shows that trained neural networks are basically equivalent to special kinds of kernel regression. So as a quick review, kernel regression, it's a classic nonlinear regression algorithm. And you can think of it as basically a way to produce output predictions by taking a weighted combination of the labels in your training data, where you use some predefined kernel function to measure the similarity between a query point and the inputs. And you learn the weighting of those similarities. You kind of memorize the weighting for every data point in your training data. The NDK result is that if you work hard and squint at this, you can show that fully trained neural networks are all technically doing kernel regression of a sort. In practice, this isn't a super useful observation all the time because kernel regression can be very slow and hard to use because you need a matrix that has as many rows and columns as you have data points. So like a million by a million matrix or a billion by a billion matrix. And then you need to invert that matrix. So that's not fun. But we found this to be a super useful tool for just doing analysis to better understand how normal neural networks like ours work in practice. So another fact from the NTK literature is that for ReLU MLPs, the kernel that the neural network is implicitly using is a kind of dot product kernel. And that means that a ReLU MLP behaves very similarly to taking a dot product of its input with all of the training data and just pushing that single scalar dot product through a nonlinearity. When your input is high dimensional, this isn't that bad a kernel. This is actually like a reasonable thing to do. But when your input is low dimensional, like in our case, you can start to see why this might be problematic. Because if I was trying to interpolate into an image and all you gave me were the dot products between the target pixel coordinate and all the other coordinates in the image, I would have a hard time designing an interpolation algorithm, right? Like that's a strange thing to do. When people usually are doing interpolation with classic signal processing techniques, they use a stationary kernel, one that reasons about the distances between the query point and all the other points. You look at your nearby neighbors and you weight them by some Gaussian distance or something, and that's your weighted function. Okay, so let's look at what dot products of Fourier feature mapped inputs look like. So here I'm just writing out the dot product from the definition. And if you apply a simple trig identity, you get this. So you see that the dot products of Fourier features of V, the dot product is actually a stationary kernel with respect to V, meaning that it's shift invariant and just depends on the distances between inputs rather than the dot product. This is not our observation. This is not new. It's been used a lot in prior works just for different tasks than ours. So, okay, so let's put these two pieces together. We know that our neural network is basically a kernel machine based around dot products of its inputs, and that the dot product of Fourier feature mapped inputs is a stationary kernel. So this means that composing a ReLU MLP with Fourier features gives us a new kind of neural network that corresponds to an NTK that is stationary. And this makes sense why this would be good, because we know from signal processing that stationary kernels are what you want to use when doing interpolation tasks, especially low dimensional interpolation tasks. So you can take this idea even further and notice that because our training data are densely and evenly distributed points in a low dimensional space, the output of this Fourier feature network is effectively a convolution with weighted deltas at each training point location. And this all nicely parallels how you would solve an interpolation problem with classic tools, right? You define some stationary kernel, like bilinear interpolation or Gaussian interpolation, and then you convolve the input with that kernel to get a smooth interpolated output that's like a Gaussian blur or upsampling. So basically, this at a very high level, this Fourier feature trick is a way to turn MLPs into interpolating machines, which they are not naturally. So here's what this looks like in practice. So this is the same sort of 2D image memorization task I showed earlier, except here we have separate training sets and test sets of pixels. So we have to worry about overfitting in addition to underfitting, like we saw before. So every other row and column is trained on. So we train on 1/4 of the pixels. So here we're seeing the output of the network at all pixels, training and test. And the Fourier feature scale, sigma, is set to a particular value. It's about 4. And you can see the image on the left looks good. And on the right, you can see a 1D slice of the composed NTK that we now know the model is using, the NTK of the Fourier features and the network together. So you can see that this kernel looks sensible, right? Like it's large at 0 and small far from 0, and it falls off like a Laplacian or a tent kernel. And that all makes sense. That's what you would probably want to use as a kernel. So now here, we've set the scale parameter of the Fourier features to be very small. And this is similar to having no Fourier features at all. So just like we saw before, you can see that the output image from the network is heavily over-smoothed. And if you look at the kernel on the right, you can see that it's extremely wide. This all makes sense, right? Because if you were trying to do interpolation with a very wide kernel, you would expect very over-smooth results. And now we know that that is exactly what is happening here. Training a network with no Fourier features is the same as doing interpolation with a over-smooth kernel. So now here I've done the opposite, and I skipped a slide. Yeah, here I've done the opposite. I've set the scale to be, the Fourier features to be very large, and this produces a very noisy image. It might be maybe illustrated by Zoom's compression, but it's very noisy on my end. In the middle, you can see the trained PSNR is very high and the test PSNR is very low, and that's characteristic of overfitting. And on the right, you can see the kernel, which is this crazy delta function. It's way too narrow a kernel to be reasonable for the sort of text. That's not how you want to interpolate. So taking all this together, you can see that when you're using these Fourier features, this scale parameter of that fixed Fourier basis is a sort of knob that I'm turning back and forth here. And this lets you tune the balance between overfitting and underfitting. And by looking at the kernel, you can see that this exactly corresponds to the NTK perspective of the problem, where you have a stationary interpolating kernel that you're modifying the bandwidth of. So this sigma is basically the bandwidth. Well, it's some function of the bandwidth of that interpolation kernel. So at first, we were just using this idea for NeRF, and it worked well. But we realized that we could apply the same sort of idea to a wide range of problems that you might see in like computational imaging or 3D vision. So we tried a bunch of experiments, and in all these setups, we just have a single scene or a single set of observations, like pixels in an image, or 3D occupancy, or even MRI scans. You could try to solve all these problems by training an implicit ReLU MLP representation of them, but it's heavily smooth, and you should never do that. It doesn't work well, so I no one ever does it. But for all these tasks, you can just add in Fourier feature mapping to the input, and suddenly this really naive baseline of just trying to solve something like MRI scanning or image super resolution by overfitting a neural network to one image actually becomes very competitive. It actually works like really well. If they're not state of the art, you shouldn't use this. If you go to the doctor, you should use the MRI algorithm they prescribe, but it's pretty good. It's a very reasonable baseline. So this image regression task comes into focus. The 3D dragon gets a lot of detail that it didn't have before. The MRI of the brain becomes clear, and of course NeRF works. So this seems like a really useful tool in a wide variety of tests. And what's really nice is it's super easy to try out. So here's what code looks like for a layer in dense neural network as usual. And here's how you add Fourier features to it. So just 2 lines of NumPy, cheap to evaluate. If you're playing with these sorts of implicit neural representations, or if you're interested in getting into it, I definitely recommend giving it a shot. It's easy to try. And you can basically prove to yourself that you have to do this, or else like NTK theory says you will have a bad time. Okay, so that's a bit on how NeRF works. Now I'm going to move to an extension of NeRF that's about how to make it more useful. So we call this project NeRF in the wild, because the goal was to get NeRF to work on the sort of unstructured, uncontrolled photo collections that you can grab off the internet. In the wild is the thing people always say for that. So as cool as NeRF is, it has a very severe limitation, which is that it assumes, or really it requires, that all the input images are basically perfect. There's no movement, there's no appearance change, etc. It also requires the cameras are calibrated, but so does NeRF-W. So we want to be able to apply NeRF to just random flicker images of some scene. We chose the Brandenburg Gate here because this was a collaboration with a team in Berlin, where the Brandenburg Gate is. As a cool side effect, the system that we get doesn't just let us move the camera like we had in NeRF, but it also lets us change the appearance of the scene, like the time of day or the weather. So our goal was basically to kind of explain those things away, or tease them apart, get rid of these confounding factors, but we actually ended up making a system that let us control them too, which is exciting. So this in the wild task is really hard, right? Because internet photos of tourist landmarks especially are a mess. They've probably been taken all at different times, so the sun might move, or lamps might turn on and off, and they could also have different kinds of post-processing applied to them by the user, or they could just have been taken by very different kinds of cameras, and they have different spectral sensitivity or different auto exposure algorithms, and that can all matter. Even bigger problem is that people generally don't take photographs of landmarks all by themselves. They might be might be people posing for the camera in front of the landmark, or pedestrians or cars moving back and forth, or flags or signs might go up or down depending on politics. So not only do we have to deal with factorizing the scene into geometry and appearance, but we also have to factorize things into static and transient components and remove these transient things that aren't always there. So here's the architecture we came up with. The input to our system is just the location of a camera and an appearance embedding, which is just a vector in a low dimensional space. This is like a GLO vector, if you're familiar with GLO. So from these two inputs, we generate a static reconstruction of the scene. And this represents the part of the scenes that's permanent, that's never going to change. So we also generate a transient reconstruction of the scene, which is contingent on a second transient embedding. And this is just meant to capture temporary structure in the scene that's specific to that particular image and isn't necessarily shared across images. To generate a final image, we just composite the static and transient reconstructions together. And this model is trained by minimizing reconstruction error against the target image in our data set. And for this to work, we also needed to modulate that reconstruction loss according to an uncertainty field that's also generated by our model and conditioned on this particular image. This allows the model to identify and ignore transient parts of the image. Basically, along with radiance, there's now this other field of kind of the standard deviation of a Gaussian, this uncertainty that exists in 3D world. And then when we evaluate our loss, we take that field, we trace rays through it, we produce renderings of these uncertainty values, and that's becomes part of our loss function. So after training, we can use our model to render novel views of the scene by giving it different viewpoints. Hopefully you saw the camera translating there. But also we can change this appearance embedding, and that lets us change the appearance of the scene without changing the viewpoint or the scene geometry. We are guaranteed by the structure of the model that this will only change the appearance and not change the geometry, and vice versa. So here's a fly-through video of that Brandenburg Gate data set. We're moving the camera, we're not changing the appearance, so everything should look kind of fixed. And it looks very nice. Definitely, if it doesn't look nice to you, please Google NeRF in the wild and check out the project page and watch the videos on the highest resolution screen you have. Here's a side-by-side with NeRF. And NeRF ends up having a lot of pretty significant artifacts because it doesn't have a way to account for transient occluders or variable appearance. You know, there's one image where someone's on the ground in front of the object, and NeRF will try to explain that person away as best it can. So it ends up hallucinating a lot of noisy structure on the ground where people are. And it also tries to explain away appearance variation using view-dependent effects. So that's kind of why it looks like the lighting is changing. If you look close, you can see the lighting changes as you move the camera around, because more pictures from one angle had a different lighting than pictures from a different angle. Here's the Trevi fountain. I think we're contractually obligated to evaluate on the Trevi fountain if we work on this task. This is the thing people love to make videos of. It looks really nice. Like in normal NeRF, we can shoot rays and see where they terminate, so we can get nice depth maps. This is probably not coming up through very well because of quantization, but it's nice on the website. And remember, our model doesn't recover just a single model of the scene, right? It's actually modeling the appearance of the scene in every individual input image. So here we're just re-rendering the scene using the same viewpoint and iterating through each of the different appearance vectors that we recovered during training. So each of these renderings kind of corresponds to the overall appearance of one image in our training data. So you can see the structure and the geometry of the scene does not change at all. And that's because it's not changing. It cannot change. It's impossible for it to change because these appearance vectors only affect color and don't affect density, because you route them down different branches of the model. Now, because these appearances correspond to embeddings in a low dimensional latent space, we can smoothly interpolate between embeddings to smoothly interpolate between appearances, like you're seeing here. So sun seems to rise and set and things like that. Definitely check out the website. Here's a comparison to neural re-rendering in the wild from CPPN last year. And you can see that our model does a better job across the board. It's much more temporally stable than NRW because we're just doing volume rendering on a static thing, a static field. But NRW has to render images by running a COM net separately in each frame. And this introduces a lot of temporal variation. So individual frames might look good, but when you see a video sequence, you can see it's clearly a neural rendering. Here's another scene, just again, we're moving the camera. So again, yeah, these results look really cool. Please check out the website to see them as best you can. And that's it. Thank you very much. Happy to take questions.
Thank you, John. Thank you for this wonderful presentation. It's been really great. And I think the results speak for themselves, really impressive results.
Thank you.
And so this is quite amazing work. For questions, we're going to have a few questions. Please, everyone, just put a little Q in the chat, then I can try to coordinate the Q&A. Yeah, Lucas has a question.
Oh, John, thank you for the amazing talk. And I'll just curate some of the YouTube questions. There's one from Dmitry Akimov who says, how does the Fourier feature approach compare to the sign activations from implicit neural representations with periodic activation functions?
Is that the Siren paper?
Yeah,
yeah, they're definitely very closely related. So the Siren paper, the network structure they have is that they have one layer of weights that are initialized to be very large, and then a sinusoidal activation, and then all the subsequent layers are initialized to be very small and also have a sinusoid activation. And so the way I think of what Siren is doing is that it's doing Fourier features at the beginning and then doing this other thing, which is to have very small sinusoidal activations. If you have very large weights and a sine activation, then your output will like wobble a lot. And if you have very small weights, then your output will just kind of be, I mean, in Siren, they set it up so the output is only kind of in this one part of the, like only in one period of the sinusoids. So Siren is definitely working well, in part because that first layer is set to be very large, and that gets around this exact same low dimensional spectral bias problem that we designed the Fourier features to get around. So I think of the Fourier features paper as being a theoretical explanation of why, of like, I would say like 60% of why Siren is working well. And in our experience, Siren and Fourier features work comparably well for all the tasks we tried. Siren is doing this one cool thing where it like reweights its weights of the subsequent layers in a way that seems to be like preconditioning. So it's doing something magical there that the paper doesn't explain. I don't have explanation for it. But this one weird trick of having a random matrix and then sign after it is in common to both. And you should think of that, the paper we have, as like a theory paper that explains Siren there. The second thing Siren does that we don't do at all is because it has a bunch of sinusoids in this network, it can train using the gradients of things. And that's a cool idea that is super relevant to some tasks and just isn't relevant to NeRF. So we haven't explored how to use that in any way. But it seems like a good idea. It's kind of orthogonal to the whole Fourier feature training thing.
John, one question about the nerves. The results you show are really great, and you showed that you can also create actual meshes out of it. So in some sense, there is a way to recover surface geometry. But I think in contrast to, say, more classical multi-view approaches, you don't actually explicitly encode the shape of the object, the surface. Do you see any downsides of not having an explicit representation of geometry in the NeRF?
Oh, definitely. Well, I would say we have an explicit model of geometry. It's just a volumetric model of geometry that is so different from classical things that it's just incompatible in a lot of ways. Yeah, no, I mean, this is a big limitation of NeRF. There are people who have tried to, actually a bunch of like people on YouTube have taken NeRF and tried to mesh them and texture them and put them into like Unity. Like if you Google like NeRF Unity, you can find kind of enthusiasts who are doing this and random stuff on YouTube about it. It doesn't look great. It's hard to make that work well. I mean, it doesn't even really solve the problem because you'd have to have like the view dependent effects baked into the mesh. Yeah, no, it would be really nice if NeRF was like backwards compatible with the Unreal Engine or something like that. That would be a really cool thing. And we are actively interested in kind of like learning how to export a NeRF. I think that, so I mean, I'm comfortable with a world in which we render images by shooting rays through volumetric things. I think that would be cool, but that's like a big disconnect from prior work. So having backwards compatibility would be nice there. It seems to be a hard problem because the geometric representation you get from a NeRF is not super smooth. There's if you zoom in, there's like lots of stuff happening. Like a flat white wall in the world in a NeRF will usually not be a flat white wall. It'll be a fuzzy, strange kind of fractal thing. So this is a harder problem than we thought it would be, and we don't have a really good answer for it yet.
I think one of the, I guess, limitations, if I may say, of the NeRF is that you seem to need a lot of views, so a fairly dense sampling of the viewing sphere, whereas in classical, say, multi-view reconstructions, often you could get away with fairly small number of camera images. Do you see ways to somehow bring back, say, like less sensitivity to the density of the sampling? How you could maybe get away with fewer views?
Yeah. I mean, we have a lot of work that's kind of actively exploring this, and there's been stuff kind of popping up on Archive that kind of is touching on this. Yeah, I mean, NeRF goes into every scene completely oblivious to the world, right? It starts fresh. The weights are completely random. It knows nothing about the world. So it definitely makes sense to explore, like, how do you learn from other images, from other worlds you've seen? How do you learn from depth maps, incorporate that knowledge in? I think that there's a lot of room for work here, and like 100 different ways to go at this problem. And I don't know what the right one is, but I think this is one of those things that a lot of people are going to be exploring and putting stuff on Archive about. So I'm excited to see what.
I mean, it definitely opens up a completely new way of thinking about the problem. Yeah. It's fascinating. Vladimir, I think Vladimir had another question.
Is it in the chat or?
Vladimir, did you want to ask a question?
Sorry, I was muted. Maybe too late to ask because you use random matrices, but before you mentioned the non-random Fourier features, and the factor of the frequencies between the resolutions was 2. Twice higher resolution, twice higher again. In the brain, grid cells, they provide kind of Fourier features to the rest of the grid cells. Yeah, they provide Fourier features to the rest of the brain to kind of encode the position of the person or the mouse in the maze and so on. And there the factor between the resolutions is, I think, the golden ratio or something like that, or square root of 5 or something like that. So every new resolution, it maximizes the amount of new information that it gives about the position. So if you just have twice as a higher resolution, you have not so much additional information, just you define more precisely out of 2 options where exactly you are. So could that be something to improve over the factor 2?
Yeah, that sounds cool. You should do that. That seems like it's worth trying. The factor of 2 thing was really just kind of motivated from this idea that there's kind of an addressing scheme in kind of like an octree, the bit string. It's like a soft approximation to a bit string that says where you are in an octree or a quad tree, and that's the most motivation. When we added more frequencies, like when we sampled the frequencies at a higher rate than 2, things got a little bit slower and sometimes a little bit better, sometimes a little bit worse. We didn't really explore this very thoroughly, but if there's a biological reason to try one thing in that design decision space, I'd say it's worth trying. I don't know very much about how the brain actually works, and I'm reluctant to speculate.
It sounds like there is a connection to the grid cells and place cells that animals and we mammals tend to have to encode space. Yeah.
Yeah.
In fact, this positional encoding trick is quite intriguing. When you first introduced it, it looked very much like the classical kernel trick where you embed things into a higher dimension to make, for support vector machines, this classical trick to make things more separable. Here, it seems to make the whole optimization problem more convex somehow. Is that right? Because the fact that you find better solutions seems to indicate that you have less, say, local minima in your learning problem.
That's interesting. I'm having a hard time wrapping my brain around the idea of there being one problem that's being kind of made more or less convex, because in my intuition is that as you change the Fourier feature representation, you just have a different problem. and it's not necessarily the same problem that you had before, and it's a problem that where optimization is better behaved. But I don't think, yeah, viewing it as in terms of local minima is an interesting way of thinking of it. We tried to basically handhold neural networks to manually initialize them to not require Fourier features. And if you think about how to do that, you basically have to like take your ReLU networks and have them have each basically approximate a sinusoid using a bunch of ReLUs, and that requires too many ReLUs to be able to do. So we decided it was outside of the capacity of a network to kind of do this well. Although I think you can maybe get it to work if you have enough capacity. Yeah, this is all very mysterious to me too. There's a lot of interest. I would love to develop a better intuition for what's going on here, because there's a lot of different lenses to view it through.
So this idea of lifting things to a high dimensional space is something that we used a lot in optimization, and there typically you can gain convexity for originally non-convex problems, but you're right, here it may be slightly different, but I think there may be analogies there. Mm-hmm.
Yeah, no, I think it's a good lens to view it through. It's just not the one we've been using. Mm-hmm. We've been trying to outsource our intuition to things like NTK and other things where we can just have we have tools that we can manipulate and like draw conclusions from. Although a lot of it's just been empirical, just trying things and seeing what works.
Oh, so there's one more question. I'm going to read it off by Simon. Sorry, he says I can't turn on my microphone. Have you tried using NeRF only with grayscale images or different color spaces, such as HSV? What is the outcome? So I think some of the images, Brandenburg, you were showing were color. Do you think it makes a difference, I guess, which color space is being used in these approaches, whether RGB or HSV or other?
There's certainly, there could be value in like having things be in like camera sensor space, because a lot of what like NeRF in the wild had to do was get around the fact that cameras are linearizing intensity differently. From RGB to YUV, I don't think there'd be any value add, because that's just a matrix multiply, and we already have an MLP that can do that if it wants to. HSV is a weird thought. I don't know what that would look like, because that wraps around on hue, so I'd be a little uneasy if I was training an HSV. If you gave it grayscale, you should expect a drop in quality, because just fundamentally every pixel is adding 1/3 as much information as it used to, and I think that will just make some things ambiguous that weren't ambiguous before. I do know that in that NeRF in the wild thing, we had lots of old pictures of the Brandenburg gate, and some of them were black and white, and it was able to just say like, this image is black and white, and explain it away. So it seems to be robust to that, but I certainly wouldn't choose grayscale if I had color available.
In the Brandenburg gate example, you showed very nicely that you can model additional effects, illumination changes, weather changes. Are there more effects that can be modeled? Time, for example. I know Noah Snavely was working on time-lapse photography, and this might be something to look into. How does a building change over time? And Noah had a nice a paper also, I think at ECCV, that was on this crowd sampling photometric function. That was like built, I think it was that paper. I might be using another paper, but he has a paper that builds directly on time and like really assumes knowledge of time. And I think that's a very reasonable idea. We didn't have good enough metadata. We just had bags of images. You need really lots of data.
Yeah.
With timestamps and everything. Yeah.
Yeah. You got to figure at some level the model is learning kind of regularities that are caused by the sun tracing the same sorts of arcs through the sky. I think that probably is getting captured by the model, but ideally we'd like to take this more into like an inverse rendering space, right? Where we actually have a notion of the sun and the scattering of the sky and the atmosphere, and then shadows being cast, and we can fake it, but we're very far away from having like a physically meaningful model that does that sort of thing.
Lucas, I think you had a question.
Yes, thank you. So I don't know if you know the NeRF++ paper from the Colton lab, but they basically argue that given that you get the color from the viewing direction, you can reconstruct any color image on a sphere just by the viewing direction. And this is not a problem in NeRF, because the viewing direction gets infused late into the network and then is implicitly regularized. The neural reflectance fields for appearance acquisition paper from also Mildenhall and others, I think they use a very explicit lighting model for each point in space. So do you think that either going the implicit direction in regularizing out these effects through the network, or going into a very explicit lighting model is the better way to go forward?
Oh, well, I mean, that's definitely not an either or. If you want a model where you have explicit notions of materials and things and you expect things to be decoupled, you will have to regularize it. I feel very confident about that. The other thing you asked was about that. We do inject the view dependent model part of the model late in the network, and that was because we thought we needed to force the model not to do that. But we actually were able to get exactly the same performance by just concatenating all the inputs as at the beginning. We just never revised the paper to do that because it didn't seem to add any value. It just made things a little bit more expensive to evaluate. The reason NeRF works is not because it's like desperately trying to, yeah, I mean, like there's definitely this failure mode that you should be worried about, which is that the model reconstructs a photograph in front of each camera. It could definitely do that. I mean, it could do that even without the view dependent thing, right? It could just put the thing right in front of the camera. But the reason NeRF doesn't do that is it appears to not be about the architecture. It's more just about like, if you do gradient descent, training is lazy. And the lazy solution for explaining away the scene is actually to get the geometry right. It's like actually very hard for a neural network to make a thin sheet of stuff that's very small and has lots of color variation and like put it right in front of the camera. That's actually just a very hard thing for it to describe, because that would be like a very small, highly detailed thing. It's not an irregularizer thing. It's actually just like a lazy training thing. And yeah, part of the magic with NeRF is that like, it just so happens that doing nothing causes the model to do the right thing. Though I do think that regularizing the model is a super interesting direction. That's a thing I'm very interested in. So I strongly encourage people to think about how to regularize them better, because I'm sure there's lots of room to be gained there.
I think that's probably a very good concluding remark, John. I think the NeRF work opens up a lot of fascinating new directions to explore. And I think we should, in the interest of time, conclude here. It's been a great pleasure having you with us today. And thank you so much for the wonderful presentation and for the very lively discussion.
Great.
Thank you so much, John.
Yeah, thank you very much. It was a pleasure. This was a fun conversation. I enjoyed talking to you all. Feel free to reach out via email or whatever if you want to discuss things further that we didn't have time to talk about.
Thank you so much. Take care, John. Bye-bye.
Bye, everyone.